We're going to start Chapter 20, Electrochemistry and Redox Reactions. We covered this before. We're going to learn about oxidation and reduction. In oxidation, you lose electrons. And in reduction, you gain electrons. So let's see. Let's take a sodium atom. And if this loses an electron, it's going to end up becoming positive. Now this electron that has been lost, it must go somewhere. By the way, since the sodium atom has lost an electron, we say that it's oxidized when it goes from sodium atom to sodium ion. Now this electron doesn't disappear, it's got to go somewhere, and we can imagine it going onto a chlorine atom to form the chloride ion. In the process of the chloride ion gaining this electron, we say it's reduced. And it's always the case, if something is being oxidized, then something else must be reduced. On the other hand, if something's being reduced, like this chlorine atom's being reduced, that electron has to come from somewhere. Electrons just don't pop into and out of existence. So in these reactions, when you're studying redox reactions, you got to remember that electrons always come from and go to somewhere. So if something's being oxidized, something else is being reduced. If something's being reduced, something else is being oxidized. Now, looking at oxidation and reduction in this way can sometimes seem a little funny, because if something is reduced, it's gaining something. And that seems a little backwards. One way to think about it is remembering that the electron is negative, and so gaining electrons is a negative thing, kind of like gaining debt is a negative thing, and gaining debt is an example of a reduction. So that's one way that you can try to remember this. The way I like to do it is to think about oxidation numbers. And in this way, if we think about oxidation numbers, it makes sense, because if something's reduced, its oxidation number goes down. And if something's oxidized, its oxidation number is going up. So we see if something's reduced, it's basically going to a more negative state. If something's oxidized, it's going to a more positive state. So the way I show this, it's going to be really important to keep track of the oxidation numbers of the chemical species that you're dealing with. And so I'm going to go over how to find oxidation numbers of elements. Now these rules that I'm going to show you, they're not like the 10 Commandments where you have to follow them all. The first one is a rule you have to follow. So let's write that one down first. So the first rule that must be followed is the sum of the oxidation numbers of all elements in a substance must equal the charge. So for example, if I'm trying to find the oxidation numbers of both sulfur and these 4 oxygens in sulfate, when I'm done assigning oxidation numbers to the sulfur and the 4 oxygens, and I add them all up, it had better equal -2. If I'm going to find the oxidation numbers of the 2 hydrogens and the single oxygen in water, when I'm done adding all those up, it had better equal 0, because water's uncharged. This rule must be followed. Now let's go over the other rules. Elements have an oxidation number of 0. Third rule, monoatomic ions have an oxidation number equal to the charge. Okay, these first 3 rules are almost always followed. The first rule always has to be followed. The rest of these are suggestions. They are guidelines, and you do them sort of in order. So first, number 4 is almost I don't want to say almost always, but is often followed for fluorine. So fluorine gets an oxidation number of -1. Rule 5, or I should say suggestion 5, hydrogen gets an oxidation number of +1. Rule 6, oxygen gets an oxidation number -2. And suggestion 7, halogens get an oxidation number of -1. Let me just show you a simple example of how we use these rules. Let's say I'm going to assign the oxidation numbers for the oxygen atoms in the oxygen molecule. Well, I have to assign oxidation numbers for both oxygens. And I'm going to add those up, and when I'm done, the total better equal 0, because an oxygen molecule is uncharged. So I know that whatever this number is and whatever this number is, when I add it up, it's got to equal 0. So let's see, I'm going to go down here to rule number 2. I wrote this here so I make sure I follow rule number 1, by the way. Now I'm going to go down here to rule number 2. Elements have an oxidation number equal to 0. Well, this is elemental oxygen. So I'm just going to put a 0 here, plus a 0 here. 0 plus 0 is 0. Rule number 1's followed, and I'm done. But notice, I violated this suggestion. And that's okay, because it's lower on the list. In a sense, these rules are listed in order of priority. You better make sure this one's followed. If I have to violate rule number 6 or suggestion number 6 to keep rule number 1 intact, I do it. So rule number 2 takes priority over rule number 6. Let's look at another example. Let's take the interhalogen compound Fi. Looks kind of weird, just IF or Fi. It would be a atom of fluorine bonded to an atom of iodine. So I'm going to need to assign an oxidation number to fluorine, and I'm going to need to assign an oxidation number to iodine, and when I'm done, it had better equal 0 because this is uncharged. So I go through the rules here. I wrote this down to make sure I'm going to follow rule number 1. This is not a pure element, so I'm not going to give either of these an oxidation number 0 because Fi is not a pure element, in contrast to O2, which is a pure element. So this second rule doesn't even apply to this compound. It's not a monoatomic ion, it's a molecule, so rule 3 doesn't apply. I get to this fourth suggestion, and I'm going to go ahead and plug in a -1 for fluorine. Well, in order to keep rule 1 intact, I see that I better give the iodine in this substance an oxidation number -1 to keep rule 1 intact. -1, that should be a +1, shouldn't it? Sorry about that. -1 plus 1, that's going to be equal to 0. So fluorine gets a -1, iodine gets a +1, and I'm done. And notice, I violated this suggestion. This is a halogen, and yet I gave it a +1 in order to keep rule number 1 intact. Let's go over some examples. We're going to find the oxidation numbers of all the elements in these compounds. Okay, actually we already did this one, didn't we? It's 0 for oxygen and 0 for oxygen, so we can cross that one out. Let's start with H2O2. We are going to need to assign the oxidation numbers for 2 hydrogens and 2 oxygens. And when I'm done, those sums, the sum of all these oxidation numbers, had better equal 0 because hydrogen peroxide is not charged. I'm making sure I follow rule number 1. I go to rule number 2. This is not an element, so rule 2 does not apply. I go to rule 3, monoatomic ions. This is not a monoatomic, so this number 3 doesn't apply. There's no fluorine, so fluorine, we don't have to worry about that. There is some hydrogen, so I'm going to go ahead and give each hydrogen a +1. Now these oxygens I'm going to have to assign the same number to because they're identical in the compound. It's not like one's going to be painted blue and the other one's going to be painted red. They're completely identical. And so if I look here, I notice that each oxygen is going to need to be a -1. 1 plus 1 minus 1 minus 1 is 0. So in this compound, each hydrogen has an oxidation number of +1, and each oxygen has an oxidation number of -1. Please notice that oxidation numbers are not charges. I want to write that down. They are a way to help us keep track of where electrons are coming from and going to in oxidation reduction reactions. All right, let's look at water. So I've got 2 hydrogens and an oxygen. And when I'm done assigning oxidation numbers, the sum of all these had better equal 0, because we've got to make sure rule number 1 is intact. The sum of the oxidation numbers of all elements in a substance has to equal the charge. In this case, the charge is 0. Water's uncharged. Water's not an element, so we're not going to even look at this rule. Water's not a monoatomic ion, so we're not going to even worry about this. Water does not contain fluorine, so we're not going to worry about this. But water has hydrogen, so I'm going to give a +1 to each hydrogen, and my oxygen, that gets a -2 then. 1 plus 1 minus 2 is 0. So the oxidation numbers for hydrogen in water are +1, and for oxygen in water is -2. And notice up here, in hydrogen peroxide, the oxidation number of oxygen is -1, and the oxidation number for oxygen in water is -2. This can happen. You can have a substance, or excuse me, an element in different substance have different oxidation numbers. And now we're already ready to look at oxidation and reduction. Watch this. Let's say I have some reaction. There's other gunk going on here, obviously, but let's just say I have some reaction where water is being transformed into hydrogen peroxide. Well, if I put in the oxidation numbers that I assigned up here for my oxygen, I notice that in order for water to go to peroxide, oxygen is going to have its oxidation number go up. It's becoming less negative. So what we say is water gets oxidized to hydrogen peroxide. On the other hand, we might have a reaction with hydrogen peroxide is going to water. And in this case, you see that the oxygen is going from an oxidation number of -1. It's going down, it's getting more negative, and it's going to a -2. So it's appropriate to say that in a chemical reaction, hydrogen peroxide gets reduced to water. All right, let's keep going. We're going to look here and try to assign the oxidation numbers in permanganate, the permanganate ion, MnO4 minus. So in this case, I'm going to need to assign an oxidation number to a single manganese and 4 oxygens. And when I'm done, the charge had better equal, the sum of these oxidation numbers had better equal -1. Well, let's check out my rules. I already did this equation here to make sure I'm following rule number 1. Permanganate is not an element, don't have to worry about that. It's not a monoatomic ion, it's a polyatomic ion. This ion is made of more than one atom. So this rule doesn't apply. There's no fluorine, there's no hydrogen. But there's some oxygens. Let's put in -2's for all of these. So all this is -8. That means manganese got to be +7 in order to make this fit. And so my oxidation number of manganese is going to be +7. My oxidation of oxygen is going to be -2 in permanganate. Now we're going to go to MnO2. Let's see what this is. All right, I have to assign an oxidation number to manganese and 2 oxygens. And when I'm done, that had no charge, so it's got to be 0. I wrote the equation to make sure I'm following this rule. Manganese dioxide is not an element, so this doesn't apply. It's not a monoatomic ion. It's not even an ion. There's no fluorine, there's no hydrogen, but there is some oxygen. So let's assign -2 to each oxygen. And I think it's pretty easy to see we're going to need to assign a +4 to the manganese in order to satisfy this equation. So in MnO2, it's actually manganese 4, it would be, in this case, manganese 4 oxide. And there could be a chemical reaction where manganese 4 oxide is getting converted to permanganate, or permanganate's getting converted to manganese 4 oxide. And we should be able to say what's happening in each of these processes. So let's see, if manganese dioxide is going to permanganate, that oxidation number is going up. So in this direction we have an oxidation. If permanganate is going to manganese 4 oxide, then in this case we have plus 7 manganese going to plus 4 manganese. We'd say permanganate gets reduced to manganese dioxide. Let's do our next one. Feo, iron oxide. It's neutral. It's got to equal 0. We're going to assign iron an oxidation number and oxygen an oxidation number. Back to our rules. I wrote the equation to satisfy number 1. It's not an element. It's a compound. It's not an ion, so we don't worry about this. No fluorine, no hydrogen, but there is an oxygen. So I'm going to give this a -2. So of course iron's going to need to be a +2. And those are the oxidation numbers for iron oxide, iron 2 oxide in this case. All right, So2 and sulfate, so sulfur dioxide and sulfate. All right, So2, we're going to need a sulfur and 2 oxygens. I'm going to add all those up, and I'm done. That better equal 0, and in this case, I got 4 oxygens. Whoop. Run out of space, so this whole thing had better equal 0 when I'm done. All right, let's see our rules. I wrote these 2 equations to make sure I'm going to satisfy rule 1. Neither of these is a pure element, so I don't worry about that. Neither of those are monoatomic ions, so I don't worry about that. Neither have fluorine, neither have hydrogen, but they both have oxygen. So I'm going to put in -2 for my oxygens. In this case, it should be pretty obvious. I'm going to put a 4 here for my sulfur. So my sulfur is going to have an oxidation number of +4. All my oxygens are going to be -2. In this case, oh boy, I put a 0 here. That was a big boo-boo. Hope you caught that. This sum has to equal -2, right? So let's see. Well, I want to save one of these -2s. So if I do a +6, that'll work, right? +6 cancels all 3 of those. So my sulfur is going to be a +6, and all my oxygens are going to have a -2 oxidation number. So I can talk about sulfate going to So2 +4 +6. If sulfate gets chemically changed to sulfur dioxide, that's going to represent a reduction, +6 going to +4. And if So2 goes to sulfate, that's going to represent an oxidation, +4 going to the more positive +6.